Okay, good morning, everyone. So last time we were talking about dipole selection rules for the hydrogen atom. And one of the reasons we're doing this, not the only reason, is because we were going to apply this to the Stark effect. But selection rules are just when you ask which matrix elements vanish for some good reason so that you don't have to bother computing them. And so in this case, we're looking at hydrogen atom states, which are characterized by three integers, n, l, and m. And the matrix element, the operator that we're interested in, is the z coordinate. And so a general matrix element looks like that. And the claim is this is non-zero only if two things are true. The first thing is that m and m prime have to be the same. Okay, and we gave the proof of that last time. And also you did a few of these for homework, so you probably noticed that if m prime was not equal to m, then this matrix element just vanished every time. Okay, so that has to be true, and it must also be true that if you look at the difference between L and L prime, it's either plus or minus 1. So I'm going to write that as the absolute value of L minus L prime is equal to 1. Okay, and so now, again, you've seen examples of this, but let's go ahead and prove it. Okay, and so the proof works like this. Let's consider the following operator, let me call it omega. Omega is going to be a double commutator. So it's going to be the commutator of L squared with the commutator of L squared with the commutator of Z, Z being the operator that we're interested in. Okay, now if you compute that, which I'm not going to do completely for you because it's not hard, but it's just a little tiny bit tedious, that turns out to be 2h bar squared times L squared Z plus ZL squared. So there's no particular trick to this. You just have to actually do the first commutator here and get the result, and then do the second commutator of that. And when you do that, you find that you can arrange the answer into this form. Okay, so this is just computation. Okay, and now what we're going to do is take matrix elements of that operator, and it's going to tell us something about the matrix elements of Z that we want to know about. Okay, so take matrix elements. Okay, and so I'm going to leave off the n in and n prime index because it doesn't do anything. It just sits there. And so we're going to be computing L prime, M prime matrix elements with omega. And the other state is Lm. Okay, and so the nice thing about this up here is we've arranged it so that in every term there's an L squared either hitting this bra or this ket. And when it's right next to this bra or this ket, we can replace it by its eigenvalue. And then once we do that, then we can do the same thing for this L squared and just evaluate it here. And the same thing with that L squared and the same thing with that L squared. So this we can just write out what the answer is. This is h bar to the fourth. On the left-hand side, there's two L squareds. Each one of them has an h bar squared. And then there's L prime times L prime plus 1 minus L times L plus 1. The minus sign comes from the fact that it's a commutator. And then you do it twice, and so it's squared. You do it twice just because of that and that. Okay, and then what's left over is the matrix element that we're interested in, namely L prime, M prime, omega Lm. Okay, so that's this side of, that's this version of omega. And then we do the same thing with that version of omega. And that gives us 2 h bar squared times another h bar squared for the L times L prime plus 1 plus L times L plus 1. And then what's left over is, again, the matrix element that we actually care about. Okay, and each one of those matrix elements has n prime equals n, but we're just not writing it down. Okay, so now if you take that whole expression and, oops, I see I made a mistake here. This omega should not have been an omega, that should have been a z. Okay, so now we can multiply everything to the left-hand side of the equation and just factor it. Okay, and so if we do that, it turns out you get L plus L prime times L plus L prime plus 2 times the quantity L minus L prime squared minus 1. All of that times the matrix element that we are interested in. All of that equals 0. Okay, so the only way that can happen is if this is not 0, or if we're going to assume for the moment that this is not 0, then this stuff has to be 0. And the only way that can happen is if one of the factors is 0. Okay, so we need, and in parentheses, by need, I mean for the matrix element to not vanish. We need one of the following things to be true. Either the first factor is 0, okay, but L and L prime are non-negative integers, and so the only way that can happen is if they're both 0. But then you can check that that doesn't work. So it's a necessary condition, but it's not sufficient, and in fact it fails. It fails because for L equals L prime equals 0, you can just compute the cos theta part of the integral, which looks like this. Okay, it's d cos theta. The L and L prime here mean that there's no theta dependence in the states. The only theta dependence is coming from the z. And so there's a cos theta here. Okay, and that integral is 0. Okay, so we can rule out that possibility. The second possibility is that this factor is 0. So that would mean L plus L prime is minus 2, but that certainly cannot happen because L and L prime are non-negative. Okay, so we can rule that out. And then the only possibility left is that L minus L prime is equal to plus or minus 1 from this factor vanishing. Okay, and so that's the only way this can happen. And in fact, that was what we claimed. If you go back up here, that was this statement. Okay, so that's our dipole selection rules. Whenever we see this, we can know that to compute it, these both must be true, that m prime is equal to m, otherwise it's 0, and this, otherwise it's 0. And for the homework that will be due a week from tomorrow, you will get to use this dipole selection rules to dramatically reduce the labor that you would otherwise have to do in order to compute some matrix elements that'll be demanded of you on that homework. Okay, so before continuing on, let me just comment that there's also a parity selection rule. So let's see what that tells us. Again, we're doing all of this for the hydrogen atom and for the operator Z. And so let's remember how that works. If we have a state of the hydrogen atom like that, and we compute parity operator Z parity operator as a matrix element. Okay, parity operator Z parity operator is negative Z. So this is minus n prime L prime M prime Z n L M. But on the other hand, we can evaluate it because we know what the parity operator does on this state and what the parity operator does on that state. Okay, and so what we learn from this is that this is equal to parity operator of NLM times parity operator N prime L prime M prime times the same matrix element. So if I move let me do it this way. If I take this and move it to the other side of the equation, then I'm getting a statement that this plus 1 times the matrix element has to equal 0. And we know from our study of the hydrogen atom what these parities are. This is always minus 1 to the L, and this is minus 1 to the L plus 1, minus 1, let's back up here, minus 1 to the L prime plus L prime. And so we need, for this to not vanish, we need minus 1 to the L plus L prime to equal minus 1. And that's just another way of saying that L plus L prime is odd. Okay, which is a nice statement. But if we think about it, it means it doesn't tell us anything that we didn't already know from the previous selection rule up here. Okay, that told us already that L minus L prime was plus or minus 1. And that already guarantees that L plus L prime is odd. Okay, so this is nothing new. It's at least consistent, which is good. But sometimes the parity selection rule will tell you something you didn't know, and sometimes it won't. In this case, it doesn't tell us anything we didn't already know. Okay, so now let's return to the particular physics problem that we were actually applying this to, and that was the Stark effect. So for the Stark effect, which I remind you means we take a hydrogen atom and we put it in an electric field so that the perturbation Hamiltonian is just the charge of the electron times the electric field that we're putting it in. We're assuming that's a constant, times the Z coordinate. Okay, and we were asking about what's the correction to the ground state energy. Which is just the expectation value of that operator. But that the expectation value of that operator in any state of the hydrogen atom is just 0. Okay, so we get first order correction to the 1, 0, 0 state, which is the ground state, is little e times big E times this expectation value. And we just showed by selection rules that that just vanishes. So that's bad news because it means if we want to know how does the hydrogen atom respond to an electric field in the ground state, first order perturbation theory is not good enough. We have to go to second order. That's bad news because it's harder, but it's not going to be impossible. We'll actually be able to get a number out of it. Okay, but the formula for the second order correction to the energy in the ground state of hydrogen is a sum over the matrix elements of the perturbation Hamiltonian, like so, with the ground state, all squared. And then we're supposed to divide by the energy difference. So that appears in the denominator. Okay, and then remember, we're supposed to only sum over things that make the denominator not vanish. So we're summing over all states n, L, and m. But I put a little prime on the sum. The prime is just a reminder that when we do that sum, we're not supposed to include the 1, 0, 0 state. Okay, so that's our sum that we have to do. And so let's notice a few things about it. First of all, the denominator here is going to be negative because the ground state here, the ground state energy is lower than all the other states. That's why it's the ground state. And so this is going to be some negative number in the denominator. And the numerator is positive, and therefore the whole thing is less than 0. So if you put a ground state hydrogen atom in an electric field, the energy gets lowered. One way of thinking about that is just it manages to arrange itself to take advantage of the fact that it's in an electric field. That will lower the energy. Okay, but the other thing is, remember our selection rules. So for example, when will this matrix element that we're talking about, when will it not vanish? Since this m is 0, that m also has to be 0 in order for this to not vanish by our first selection rule. And because this L is 0, that means this L also has to be 0 or it will vanish. Okay, so we really don't have to sum over L and M, we only have to sum over N. Okay, so to write that, since we know it's negative, let me compute it as the absolute value. Just because we know it's negative. Okay, and then I'm going to pull out the factors of little e squared and big E squared. And then there's a sum over n, but we know we don't have to include n equals 0. So this is a sum over all n not equal to 0. Or sorry, not equal to 1. 1 is the ground state. And then the matrix element we're including here looks like this. Okay, and I might as well put in the ground state energy, which is E squared over 2A0. That's actually negative the ground state energy, but I took the absolute value on the outside. And so I'm really multiplying by -1, which means now I add in the unperturbed energy of the NLM state, which I should not have written that way. I should have written N10 because that's the only thing that contributes. Okay, so unfortunately, we have to compute an infinite sum there, which is not the easiest thing in the world. And so it's what we're actually going to do is we're going to put some bounds on this, and then I'll just quote you the exact answer for this infinite sum, which is kind of non-trivial. So let's consider ways to put bounds on this sum. And the first thing to notice is that all terms in the sum are the same sign. In fact, they're all positive. So note, all terms in sum are positive. And the reason for that is, again, because we happen to be computing something for the ground state. And so the unperturbed energy of any other state is greater than or equal to the ground state energy. And in fact, it's greater than or equal to minus E squared over 2A0. That's the Rydberg energy times a quarter, because the lowest n that can contribute is n equals 2 here. And so we plug in 1 over n squared to get the energy of the hydrogen atom in that state. So what that means is we can get a bound this will be larger than what we would get if we only included the n equals 2 term. So we can certainly say that if we just threw away everything else and just looked at the n equals 2 term, it's got to be greater than that because all the other terms are the same sign. Okay, and so now we can evaluate that. It's just one term, so it's not too hard. So we're just writing that down. And then the energy denominator, because we're plugging in n equals 2, looks like this. Okay, and when the dust settles, we get 8/3, let me write it down here, 8/3 the Bohr radius times the electric field squared times the square of this matrix element. And then what makes this even easier, so this matrix element, let me call it question mark. What makes this even easier is that I had you do it for homework. And so question mark is actually equal to 128 square root of 2 over 243 times a Bohr radius again. So it's always nice when you've done it already for homework. That means we have a bound on the energy correction at second order in perturbation theory for the ground state, which is it's got to be greater than the electric field squared, the Bohr radius cubed, times, it turns out when you square 128 square root of 2 over 243 and multiply by 8/3, it's 262,144 over 177,147, which is, and I'm not sure what the deep reason for this is, but it seems like it's always powers of 2 and 3 to ridiculously large numbers. In this case, it's 2 to the 18th power over 3 to the 11th power, which is approximately 1.48. So it's 1.48, the electric field squared times the Bohr radius cubed. So if I just gave you that formula and I didn't tell you where it came from, you should be able to know immediately that it came from second order in perturbation theory. And the reason it's second order in perturbation theory is just it's proportional to the perturbation, the electric field, squared. Right? And it's also proportional to basically the volume of the hydrogen atom. Okay, so that's one way of getting an estimate. We've proved the energy correction has to be larger than a certain amount. Okay, and we can also show that it has to be less than a certain amount because the denominators are positive, but they're getting smaller as you go to larger n. So this is sort of another thought here. Because denominator or denominators e squared over 2a0, that's the ground state energy in absolute value, plus an unperturbed energy, that's always greater than e squared over 2a0 times 1 minus 1/4. That's what we actually put in for the n equals 2. That means the energy correction in absolute value has to be less than, I'll write it in words here and then we'll evaluate it. It has to be less than the sum with all terms replaced by a larger number, in this case, e squared over 2a0 plus the unperturbed 210 state, and that's 3e squared over 8a0. Basically the same thing we just put in previously. Okay, so that's going to give us a bound uh, as follows. Let's just go ahead and make that replacement. So the absolute value of the second order correction we now know is less than 8 Bohr radius over 3 electric field squared. And now the sum that we're going to put in here is a sum over all n's not equal to 1, n, oops, n10, z100 squared. Okay, so why did we do this? Again, the strategy is just that by approximating the denominator and doing it in such a way that we can bound it, then we get the denominator out of the sum, and now we're actually going to be able to compute this sum. So how are we going to compute it? The first thing we're going to do is notice that it almost looks like it's ready to use completeness on it, because we're summing over what will essentially be a complete set of states here. The only problem is that we've excluded something from the complete set of states, and so it doesn't quite work right away, but it will work if we rewrite it. So I'm going to rewrite it as a sum over all n of the same thing, and I'm going to rewrite the same thing like this. Okay. So the only problem is now we've included one term that we weren't supposed to include, namely the n equals 1 term, so we better subtract that off. Okay, and now we really can use completeness on this. And so in fact, by using completeness, what we're really noticing is that the sum over all n of this is just the identity operator. And so we can rewrite this as 100 z squared, 100. And this, our dipole selection rules told us was 0 anyway. So we wrote it there just to make sure everything was allowed and worked, but it didn't contribute. Okay, so now we have to evaluate this matrix element. So I'll call that question mark. And unfortunately, I didn't have you do that one for homework, so let's do it really quickly now. That's equal to, in position space, we integrate over all r's with an r squared. We integrate over all phi's from 0 to 2 pi. We integrate over cosine theta from -1 to 1. Okay, and then we write in the ground state wave function squared, which is 1 over pi Bohr radius cubed, e to the -2r over Bohr radius. And then finally, we write the representation of the operator z squared, which is r squared cosine squared theta. Okay, so that's the integral that needs to be done. The easy part is the phi part, which is just a factor of 2 pi. The next easiest part is the cosine theta part, which is going to give you a factor of 2/3. Okay, and so now we can clear out all the constants out front, and that gives 4 over 3 Bohr radius cubed, and what's left is the r integral. It's r to the 4th, e to the -2r over Bohr radius. Common mistake not to make is to forget the r squared in the volume element. Okay, and then you can do that integral or look it up, and the answer is 3 Bohr radius to the 5th over 4. And so the whole thing is remarkably simple. It's just the Bohr radius squared. Okay, so we've successfully done this matrix element by reducing it to an integral. And so now we have a bound that says the energy correction has to be less than just that times the Bohr radius squared. Okay, and so we've got that the energy correction is, actually, let me write it as a double-sided bound because we already had this bound up here. Oops, I didn't mean that. We had this bound up here. And so that number is, what was it, 1.48? So we have 1.48 Bohr radius cubed e squared is less than the energy correction that we're looking for. And that's less than 8/3 Bohr radius cubed over e squared, or times e squared, which is about 2.67 Bohr radius cubed e squared. Okay, so we've got the answer bracketed between those two things. And the only way to do better than that is to just go ahead and compute that sum. Okay, and so let's consider what we get when we do that. Turns out there's a famous trap that you can fall into when you try to compute this sum. So let me write it again, the general form of it, and then I'll explain the trap. Okay, so it's a sum over all n not equal to 1 of n10 z100 squared over this energy denominator, e squared over 2a0 minus curly e n10. So here's the trap, is a lot of times when we're talking about the hydrogen atom, all we care about is the bound states. Because if you have a transition between two states, for example, by emitting a photon or absorbing a photon, a lot of times it's just going back and forth between two bound states. But according to what we calculated in our general version of perturbation theory, there's no reason to exclude the states that aren't bound states. And so the note here is that we shouldn't do that. This should include as well the continuum states that have positive energy. Now, when we derived our bounds just a minute ago, we used inequalities. So we weren't leaving those states out. But now, naively, if you were to go ahead and start computing terms in the sum, you would never, just by including the bound states, you would never get the correct answer. So it turns out there's a clever method, which we're not going to take the time to go over, by Dalgarno and Lewis, who actually showed that you can do this sum. This was in 1955. And they showed that you can do this sum exactly, and including the continuum states as well as the bound states, and get a remarkably simple answer. It turns out to be it's e squared times 9/4 times the Bohr radius cubed, which is about 2.25 Bohr radius cubed e squared. So sure enough, as promised, 2.25 is between 2.67 and 1.48. So that's true, that's good. And in parentheses, I'll just mention what would happen if you forgot to include the continuum states. If you add up only the bound states, it actually turns out it's not as nice an answer. It's harder to even write down what it is, but you can do it numerically. So bound states means the unperturbed energies are negative. Then you would have gotten about 1.832 Bohr radius cubed times e squared. So that's the wrong answer. It also happens to be between the two bounds. Okay, but that's just not the right answer. All right, so now let's just go ahead and use the correct answer, which is this, for the second order correction to the energy. And let's notice how you would actually measure this in an experiment. So the way you would measure this is you would notice that the energy had decreased. And the reason it decreases, you can discuss even classically as the fact that you have induced a dipole moment. Okay, so the dipole moment, classically, the electric dipole moment, there are too many things called P, so we also use P for dipole moment because it's traditional, but it's equal to something, a constant, times the electric field, and the constant is called the polarizability. Okay, but to relate that to the correction in the energy that we just found, we remember from classical electromagnetism that the energy of a dipole in an electric field is given by, well, it's easier to first write down the change in the energy. So the change in the energy is minus the dipole moment dotted into the change in the electric field. So for us, that's going to be minus the polarizability times the electric field times the change in the electric field. They're in the same direction, so the dot product just gives 1. Okay, and so if you integrate that, you find that the energy associated with the dipole is minus 1/2 polarizability times the electric field squared. So indeed, we found that the energy got more negative. That's this minus sign. We found it was proportional to the electric field squared, so that's good. And then by comparing how negative it got, we can pick off the value of the polarizability. And the polarizability is something that people can go off and measure. So just to summarize that, if we compare what we actually found to the general formula that says what polarizability is, we're getting minus 9/4 from Dalgarno and Lewis. A0 cubed e squared should equal minus 1/2 the polarizability times e squared. And so that tells us the polarizability of the hydrogen atom in its ground state is alpha equals 9/2 Bohr radius cubed. And now you can just plug in the numbers. We know numerically what the Bohr radius is. And so this turns out to be 6.67 times 10 to the minus 31 meters cubed. And now you can go get yourself a big bottle of hydrogen gas and put it in an electric field and compute the polarizability and measure the polarizability. And it turns out this works extremely well. So this is a very good approximation. And you could say, why wouldn't this work? There's only 2 reasons why it wouldn't work. There are 2 obvious reasons. One is because not all of your hydrogen atoms will actually be in the ground state. You have a big bottle of hydrogen gas. Some of them will be in an excited state. And the other reason is because this was an approximation because it was second order in perturbation theory. And to really get it right, you should include maybe third order in perturbation theory and fourth order in perturbation theory. And you'll be happy to know that we are not going to do that. That correction turns out to be very small. So the more important effect is that some of your atoms won't actually be in the ground state. So let's think about that. some of them will be in the n equals 2 state. So let's compute the same thing, and that's called the linear Stark effect. Okay, so for the n equals 2 state, there's actually 4 of them. So the unperturbed states look like the following. In NLM notation, they are 2, 0, 0, and 2, 1, 0, and 2, 1, 1, and 2, 1, minus 1. Okay, the degeneracy of the n level is always n squared, so that's all of them. And they all have the same unperturbed energy. So we need to use degenerate perturbation theory, which might sound like bad news, but it's actually good news. It actually makes things easier. So remember, in degenerate perturbation theory, the first step that we're supposed to do is we're supposed to take the perturbation Hamiltonian only on the subspace of the unperturbed states that are degenerate and choose a basis such that it's diagonal. So what does that mean? That means we need to look at a 4x4 matrix and that's one of the reasons it's easier is because in the thing that we did at the n equals 1 level, we had to sum at second order in perturbation theory over a whole bunch of other states. But here, all we care about is 2 L prime M prime. There's the perturbation Hamiltonian, 2 LM. Okay, and the dipole selection rules tell us a lot of those are 0. So naively, there are 4 times 4 equals 16 things to compute, but about half of those are just complex conjugates of the other half because you know that Z is a Hermitian matrix. Okay, and so the only non-zero elements are 2, 1, 0. I'm just going to put the Z there, 2, 0, 0. Okay, and it's complex conjugate, and this thing will turn out to be real. So it's 2, 0, 0, Z, 2, 1, 0. Okay, and fortunately, I also already had you do that one for homework. And so we already know that one is -3 times the Bohr radius. All of this is for the hydrogen atom. Okay, and so the matrix representing the perturbation Hamiltonian W is this. So there's a -3 times the Bohr radius, and then we can't forget the factor of little e times big E. Okay, and then the matrix has the form that it's almost all zeros. In fact, the dipole selection rule says all the diagonal things are 0, and there's a 1 here and a 1 here, and everything else is also zeros. Dipole selection rules are a great thing, right? And this is in the basis of where I've put the entries in the matrix in the exact same order given here, right? So the only things that are non-zero are the things that connect this state with that state. That's the off-diagonal things here. And then these states just don't get any non-zero matrix elements at all. That's why all of these are 0 and all of those are 0. Okay, so the first thing we're supposed to do is we're supposed to compute the eigenvalues of this matrix. So the eigenvalues are the first order corrections to the energy. Okay, and so they are plus or minus 3 Bohr radius little e times big E. That's 2 of them. And then there's another one that's 0, and there's another one that's 0. Okay, and so at first order in perturbation theory, we found a non-zero effect. And so that's why it's the linear Stark effect. It's first order in perturbation theory. And we now know the first order energy states, and you can also get the energy eigenvectors from this. And so to summarize it, for energy equals, I'm going to write down minus E squared, that's a Rydberg, times 1/4 because it's n equals 2, minus 3 A0 little e times big E. So we've subtracted off something, and therefore this will be the lowest energy state among the n equals 2 states after we add an electric field. And it's 1 over the square root of 2, 2, 0, 0, plus 2, 1, 0. It's a linear combination of those two L states. Okay, and then there's the same thing, but we're going to add a little bit. So this is the highest energy of those states, and it's the other linear combination. Okay, and then there are these other two states that don't get affected. So they just stay the same, and that's the states 2, 1, 1, and 2, 1, minus 1. Okay, now this is just adding in an electric field, and so those states stay degenerate. But to know that they're there, what you can then do is you can put your atom in a magnetic field. The magnetic field will split this state here slightly apart from that state there, and you'll be able to see that there are in fact 2 of them by the fact that they get split apart slightly in a magnetic field. Okay, and so now if you were to make, for example, a graph of the energy versus the electric field that you're adding, there are too many things with E, but that's the way things go. Then the ground state down here, the n equals 1 state, goes quadratically. So it takes some time to turn on, but then its energy goes down. And the n equals 2 states go linearly. So pretend what I'm about to draw is perfect straight lines. Okay, and so this is the linear Stark effect is at the second level, and this is the quadratic Stark effect. That's what governs the ground state. Okay, questions on that? All right, so it's important to notice that, by the way, everything we did was just completely wrong. Now, what do I mean by that? In this example, perturbation theory actually does not converge. So perturbation theory does not converge. Remember, we're assuming, whenever we do perturbation theory, we're assuming that we can do a series and that the series converges, and in this case, it just doesn't. So why doesn't it converge? If we graph the potential that we're actually putting our hydrogen or electron in the hydrogen atom in, it's got 2 parts to it. So this is our potential energy. I'll just write it as V. So first of all, and I'm going to graph this as a function of Z rather than the radial coordinate the way one usually does. So this is one slice through space. And so there's the Coulomb potential from the proton's electric field, which looks like that. Okay, but now we've added an electric field that grows linearly. So it does something like that. Okay, so this is W equals E times big E times Z. And this is the potential down here. This is the potential V of R from the proton. Okay, and so the thing to notice is that if your electron manages to wander very far away, then it's always true that these extreme values very far away for the potential are going to dominate over the potential from the proton. No matter how weak you make the electric field here, it's always going to be true that if you go far enough away, this will dominate. And so what that means is for the problem that we actually claim to do, there are actually no bound states at all. And so when we tried to compute what they were, we were cheating. So that might sound like bad news. And why did we bother? And why did we actually get the right answer for the polarizability? And the answer is because in the real world, there's no such thing as an electric field that extends infinitely far away. So in the real world, what we actually did in perturbation theory was correct. And the exact answer that would have given no bound states is what's incorrect. Sometimes it's better to make an approximation. And this is a good example. So in the real world, you actually cut off the electric field. It doesn't extend infinitely far. Okay, and so what's really going on is this, instead of going infinitely big, gets cut off at some value. Okay, and then perturbation theory converges and gives the right answer, and gives the answer that we actually got. Or gives an answer very close to what we actually got. And so everything we actually did was okay, even though as an idealized problem, it was completely wrong. Okay, so that's the good news. And so that's all we have to say about the Stark effect. And next time we will be talking about almost degenerate perturbation theory and see what happens there. Okay, any questions about today's lecture?
Professor?
Yes.
I got a question about, yeah. So this perturbation theory converging, so that means something, it's cut off. Is that what it means? Or is this just an
Perturbation
example
theory
of it?
converges just means the infinite sum we did over lambda when we started out is actually going to be a series that converges to a finite number, rather than either going off to infinity, which it could do, or oscillating wildly and never settling down to some number. Those are both ways that a series could fail to converge. Okay, and so if you put in an idealized electric field that grew without bound, or so that the potential grows without bound because the electric field is constant throughout the entire universe, then what I'm claiming here is perturbation theory would not converge at all. And so we would be doing the wrong problem. But fortunately, that's not what happens in the real world. In the real world, if you go off 1 meter for a hydrogen atom, then your electric field experiment is cut off there. And so there's no problem.
Thank you.
Sure. Other questions? All right. So if not, you have homework that is due tomorrow. I guess we decided homework's due now Thursdays at midnight. And there is already a homework set 3 on the website, which is due a week from tomorrow. So look for that and don't forget to download it. All right. So if there are no other questions, everybody have a good day.
Thanks. Have a good one.